Hi, in this video we are going to talk about KMP string matching algorithm. So the problem is we are given a text and a pattern. We need to find out where all this pattern is present in the text. In this example, pattern is present in index 1, right? This is index 0, this is index 1 and your whole pattern is present here. So our output is 1. Let's see this example. In this example, our pattern is 4A's and our text is 5A's followed by B. So pattern is presented index 0, right here, and also presented index 1 here. So our output is 0, 1. In this example, the pattern is not present. BA is not present at all, right? So our output is not found. We have already talked about some algorithms to solve this problem. We talked about naive algorithm, which is quadratic in time. Then we talked about naive algorithm for distinct characters. If your pattern contains distinct characters, then you can optimize the naive algorithm to work in big O of n time. Please note that n is the length of text here and m is the length of pattern here. Then we talked about Rabin-Karp algorithm, which is also quadratic in worst case, but Rabin-Karp algorithm works better than naive in general. Rabin-Karp algorithm uses the idea of rolling hash. In this video, we are going to talk about KMP algorithm. KMP algorithm takes big O of n time and requires big O of m auxiliary space, where m is length of the pattern. The main idea of KMP algorithm is to pre-process the pattern and then do the pattern searching. And KMP algorithm does pattern searching like naive algorithm. It slides the pattern over the text one by one and then finds all occurrences of the pattern. When we will do the time complexity of KMP algorithm, we'll see that it does at most 2n work. The loop inside KMP algorithm does at most 2n time, where n is the length of text. In this example, naive algorithm first started with window at shift 0, did 4 comparisons, then shifted the pattern by 1 and again did 4 comparisons, then shifted the pattern by 2 and again did 4 comparisons. So how many comparisons naive algorithm did here? 4 plus 4 plus 4, 12, which is n minus m plus 1 into m in the worst case. That's the worst case number of comparisons that your naive algorithm is going to do. Let us now get an idea of KMP string matching algorithm. How KMP is going to work better than the naive for this particular example. In KMP algorithm, we first pre-process the pattern and build an array called LPS. The size of this array is same as the size of this pattern. There are 4 characters in the pattern, so this array is of size 4. And this is an integer array. LPS ith element in this particular array stores the longest proper prefix of pattern from index 0 to I, which is also a suffix of the same pattern here. We have discussed LPS computation in detail in the previous video. How do we get these values and how to fill this LPS array in linear time. Let us now see how KMP algorithm uses this LPS array to find the pattern. Like naive algorithm, KMP also begins with I equal to 0 and j equal to 0. J is going to be an index in the pattern and I is going to be an index in the text. It matches text I with pattern j in every iteration. And here they match. I is 0, j is 0, so they're matching. Now we increment both I and j. We come here and we match these two. So I is now 1 and j is now 1. So I is here and j is here. So they are matching again. So we again increment I and j. This is similar to naive algorithm. What we are doing here is same as naive algorithm. They are matching again. Now we again increment I and j. So they are matching again. So we come here. Right? And now we see that we have matched all characters of the pattern with all characters of the current window of the text. So we say that we found the pattern at index 0 and our output is going to have 0 as the first thing. We are going to print 0 as the first occurrence of the pattern. Now the question arises, what should be the next characters to be matched? We have matched all the characters. What were we doing in the naive algorithm? We were going to compare this character and this character in the naive algorithm. And this is where KMP algorithm does optimizations using this LPS array. What it does is, it looks up the value for the last matched character in the LPS array. Last matched character is the last character, right? Last character of the pattern. So this particular LPS value is looked for finding the next indexes to be matched. This value is 3. So the index of the character that we need to match in the pattern is 3. This is the next character that we need to match in the pattern. And in this particular text, we always increment the index by 1 whenever we see a match. So our next characters to be matched are this and this. Right? In text, the rule is simple. Whenever you see a match, you always increment the index. In pattern, we use the LPS array to find the next index. And we got the index as 3. So next time, we are going to match these 2 characters only. We are not going to match all the 3 characters. This LPS array actually tells us that these 3 characters are anyways going to match these 3 characters, and there is no point matching them unnecessarily. And with the help of LPS array, we save all these 3 comparisons, and we are going to mainly compare this character with this character next time. And how did we get the index of this character? We used LPS value for the last matched character. Now let's understand how does this LPS array helps us in skipping these 3 matches that we were doing in the KMP algorithm. What is the meaning of LPS? LPS means at this index, which is the index of last character, which means here, the length of the proper prefix, the longest proper prefix, which is also suffix, is 3. Which means these 3 characters are same as these 3 characters. They are same. Right? They are same as these 3 characters. This is longest proper prefix length 3 and this is suffix also 3. And now if we leave this LPS array for some moment and if we take a look at the pattern and text KMP algorithm, why did we consult the LPS array? Because these 3 characters had matched these 3 characters, right? So these 3 characters are same as these 3 and these 3 are same as these 3 because of LPS array telling us, right? Which means they are going to be same as these 3 characters because they are same as this and they are same as these. They are same as these is told us by LPS array, and they are same as these we figured out because we were running the KMP loop and we were matching the characters one by one. So that is how we skip matching these 3 characters with these 3 characters. We do not have to match them. We just need to match these 2 characters. Why are we not matching these 3 with these 3? Because they will anyways match. You know, LPS array is telling us that they will match. No need to match them again unnecessarily, right? So we simply match these 2 characters. We find a match. And since this is the last character of the pattern, at this moment, we simply print output as 1. We found the pattern at shift 1. Now again, which character should we match? We again consult the LPS array. And LPS array tells us that LPS value of the last matched character, which is A, is 3. So you again need to match the last character of this with the next character in the text. Next character in the text is B. Now you are going to slide the pattern this way, right? And you are going to match this A with this B, right? And this LPS array tells that you do not need to match these 3 characters with these 3 characters. They will anyway match. No need to match them again unnecessarily, right? And since they do not match, you do not print this particular shift as part of output. Please note that naive algorithm also works in linear time when all the characters in the pattern are distinct. It starts taking more time when there are redundancies within the pattern. And that's the whole idea of KMP algorithm. It pre-processes the pattern, which is basically pre-processes the redundancies within the pattern so that the worst case time remains linear. Let's now take a look at detailed algorithm. So we have written code here, which is a pseudo code close to C++ and Java programming language codes. We are passing 2 strings to this function, pattern and text. As a first step, we are finding their length. N is the length of text and M is the length of pattern. After that, we build an auxiliary array, LPS, and we fill this array using the fill LPS function. We have talked about this function in detail in the previous video. So this is all pre-processing part. Now begins the comparison part. we initialize I equal to 0 and j equal to 0. And then we run a loop while we have not reached the last character of text. Inside this loop, we keep on incrementing I and j if pattern j matches with the text I. And if we matched all the characters, if j became m, then we print the shift as I minus j, right? Or you can write I minus m also, because I is the current character and you will find the beginning of this shift by doing I minus m. And then we use LPS array to find the next value of j, right? That is something we discussed and checked in the previous example. If the current characters do not match, then we have two cases. If j is 0, if it was the first character that we were trying to match and this first character itself did not match, then simply move ahead in the text. Simply do I++. And this is the case where there was some matches and after some matches there was a mismatch. So we do same as we did here. Whenever see a mismatch after matches, we consult the LPS array to find the next character in the pattern to match, right? So this is the trickiest part here and here. They both are same. And this also is the case when you have already matched certain characters. In fact, you have matched the whole pattern and now you are trying to find out next value of j after certain matches. And this is where also you are trying to find out the next value of j after certain matches. If you take a look at this algorithm, it looks very similar to what we discussed in this fill LPS function in the previous video. Fill LPS also uses the idea of this KMP algorithm to fill the LPS array. Let's now do a dry run of this algorithm for this particular example. So this is our text and this is our pattern. Length of this text is 12 and length of the pattern is 5. And we have built LPS array for this particular pattern. And now we are going to begin with I equal to 0 and j equal to 0. Right? So we are here in this algorithm. And inside this loop, we compare pattern j with text I. So we compare the first characters. They're matching. So as long as the characters are matching, we keep on doing I++ and j++. Matched, we came here. We now have I equal to 1 and j equal to 1. So they also matched. Now we have I equal to 2 and j equal to 2. They also matched. Now we have I equal to 3 and j equal to 3. They also matched. Now we have I equal to 4 and j equal to 4. And when I is 4 and j is 4, they do not match. Right? So we come into this case that characters do not match. And which case we are in this particular case? There are two cases in this. J is not 0, right? So we are in a case when we have seen a mismatch after certain matches. So we consult the LPS array to find the next value of j. And to consult, we go to the index of last matched character. Last matched character is j is 3. So at j equal to 3, we have 2 in the LPS array. So j now becomes LPS of j minus 1, which is 2. Right? So we have this j as 2. We have brought the pattern here. We did not change I. We simply changed j equal to 2, which means the pattern has come here. These two characters need to be matched now. Right? So this is our current I and this is our current j. Right? J is 2. And I just brought this pattern such that j equal to 2 comes just before the current I. Now we are again going to compare these two characters. And these two characters again do not match. So we are going to consult the LPS array to find the next shift. And last matched character was this one. So we are going to get the j as LPS of j minus 1. So j minus 1 is 1. J was currently 2. So LPS of 1 is 0. So this time we are going to bring this character a below it and then we are going to compare them. Now I have written the 0th character below current I, right? And now we are again going to compare them and they do not match. If they do not match, we have two cases and this time we are in this case. because j is 0. So what do we do now? We increment I. We bring I equal to here, right? And we do not change j. J remains 0. So next time we are going to compare these two characters. So now we are at I equal to 5 and j equal to 0. I have rewritten all these steps for your reference. We started with I equal to 0 and j equal to 0. They were matched. So we incremented I and j both, then again matched, so we incremented I and j, again matched, we incremented I and j. And this time they mismatched, right? So we saw a mismatch at I equal to 4 and j equal to 4, right? And at this point, we consulted the LPS array to find the next j, and we found the next j as 2, and we compared text of I and pattern j again, and they did not match. So we again consulted LPS array and we found j equal to 0 and we kept I equal to 4. And at this point we again found a mismatch. But this time j was 0, so we changed I. Now we are here at I equal to 5 and j equal to 0. Now we see a match, right? So we are going to increment I and j both. Now I is going to become 6 and j is going to become 1. Right? So I and j are changed. They are here right now. Now I and j again match. So we are going to make I equal to 7 and j equal to 2. They again match. So we are going to make I equal to 8 and j equal to 3. They again match. So we are going to have I equal to 9 and j equal to 4. And they also match. So we are going to have I equal to 10 and j equal to 5. So j now becomes m, which is the number of characters in the pattern. So we fall into this particular case and we print I minus j or I minus m because j is m right now. So what is I minus j? 10 minus 5. So we are going to print 5. We are going to tell the output that we found the pattern at index 5. And you can notice that this pattern is presented at this index, which is 5. 0, 1, 2, 3, 4, 5. So we print 5 on the screen. After printing 5 on the screen, we again consult the LPS array for next value of j. Now we need to find out LPS of j minus 1, which means LPS of 4. What is LPS of 4? 0, 1, 2, 3, 4. It's 3. So we are going to have j equals to LPS of 4, which is 3. Let's now shift according to new I and j values. Now I have aligned I equal to 10 with j equal to 3. And this time we again see a mismatch. So what are we going to do? We are going to consult the LPS array and we are going to look at LPS of j minus 1, which means LPS of 2. LPS of 2 is 1. So our j now becomes 1. Now let us align first character with I equal to 10. Here I have aligned I equal to 10 with j equal to 1. These two characters again do not match. So we are going to consult the LPS array. We are going to look at LPS of j minus 1, which is LPS of 0. And LPS of 0 gives us 0. So we are going to make j equal to 0 now. And we are going to keep I as 10 only. Now I have aligned for I equal to 10 and j equal to 0. At this point, they are matching. So we do I plus plus and j plus plus. Our new I becomes 11 and j becomes 1. And we see a mismatch. These two do not match. I equal to 11 and j equal to 1. They do not match. So what are we going to do? We are going to consult the LPS array. Right? We are going to find out LPS 0, which is a 0 value. So we are going to update j as 0 and we are going to keep I as 11. Now I have aligned for I equal to 11 and j equal to 0. So this is our text and this is our pattern. Text is at I equal to 11 and pattern is j is equal to 0. So we are again going to compare text I with pattern j, and this time they do not match, and this time we have j equal to 0. So what are we going to do? We are going to make I equal to 12. Now when you make I equal to 12, the loop will not run again because I should be smaller than n. And at this point, KMP algorithm stops. Let us now talk about time complexity analysis of KMP algorithm. If we take a closer look at this loop, we can notice that in every iteration, we are moving ahead in the text or we are sliding the pattern ahead. When you do I++, J++, you are simply moving ahead in the text one by one. And when you do any of these two operations, this or this, you are sliding the pattern ahead. For example, here J was 2 and you changed to J equal to 0 using this thing that they're not matching, so you change it. And what it effectively means is you slided the pattern 2 positions ahead, right? And you're sliding this pattern over the text. So how much maximum you can slide? You can slide it at most n times, right? You begin with from here, then you slide here maybe, and then slide here. Even if you are sliding one by one in the worst case, you will slide at most n times. And how much you can traverse in the text if you are doing I++? It's the length of the text. Your I begins with 0 and then you go up to n-1. So you are doing n work for traversing through the text and n work for sliding the pattern over the text. So overall work done by in this KMP algorithm is upper bounded by 2n, where n is the length of text.